Okay. After opening the software, the first thing we need to do is set up the instrument portion of the method. So I'm going to come over here to the GC, double click on the GC, and it will connect to the instrument. You should hear a beep. Also make sure all your gases are on, there's plenty of gas, and that all the valves and check stops are open. Otherwise you'll have problems down the road. And that the FID pressures are set correctly, because in this instance you have your FIDs are not controlled, I believe, by a gas controller. So you have to set your FIDs manually, which would be your air and your hydrogen. So make sure those are set correctly on the gauge on the back of the GC. So I'm going to resize this a little bit, and we're going to enter the parameters that we pull from the method. So let's go up. Okay. So the first thing again is we do the SPL, the flow rate here. Now in the method that we looked at, that temperature was 180 degrees. And they were doing split. So you want to make sure you have it set to split. Then down here, you can see you can do column flow, pressure, or linear velocity. They were using a linear velocity here of 25, which is relatively low, but depending on the complexity of the separation, you may need to go that low. Typically, you want to get things through the column as fast as possible without sacrificing resolution of compounds. That being, if you have a lot of compounds and you force it through the column too quickly, they're going to co-elute. So that's what we have there. And then the split ratio for this here was 20. Now, I typically, in that instance there of the method that we had looked at, they had a 20-to-1 split ratio, but they were injecting half a microliter. So I would probably change this to 40 and inject a full microliter. Again, we want to make sure that we are not overloading the column. So by using that, that will keep things consistent based on that. So we have this done. Something else that's critical, and I want you to do, is make sure you have the carrier gas saver turned on. And after a minute, let's go to a 2-to-1 split ratio. So basically what this is going to do is it's going to save you a lot of carrier gas. You can see currently when you're running here at 40 mils a minute at a split ratio of this, you're running 45 milliliters per minute through the run. Say you have a 10-minute run, that's going to be 450 milliliters per sample, at least, because you have to also get into the lower go back down to your original starting temperature. Okay, so if we set that to 2, after a minute, our flow rate goes down to 6 mils. So you're running 72 plus the 40. So basically it's 100 mils for an entire run versus almost 500. So you're saving a lot of gas. So make sure that is turned on. I'm going to change this back to 40, but I was just showing you that if you change this, it will let you know your total flow here and set that accordingly. So always make sure your carrier gas saver is on. After a minute, typically everything is on the column. So I would definitely set that. Okay, so that part is done. We have the flow set correctly based on the method. Now we're going to go to the column. Here's the column. Now in here you want to make sure you won't be changing columns out. But again, if we go back here to this is all based on the column. And by that I mean the length of the column and the inner diameter of the column will provide a very specific resistance. So based on that resistance calculated in the algorithm, we know a certain pressure is required at a specific temperature to push things through at the specified linear velocity. So in here the column has to be correct, specifically the inner diameter and the column length. Again, you probably won't be changing that. Okay. Now here we have our starting temperature. What is the oven's initial temperature going to be? Now, in the method that we looked at, it was 35 degrees. So it's at that 35 degrees. The other thing you have here is the equilibration time. This is the time between which, at the end of a run, it has to come down to the initial temperatures and it lets things thermally equilibrate. 3 minutes is a little bit longer than I like. 1 minute should be sufficient. So that's what that is. Now, over here, we look at the method more. And if you remember from the method, we had it 35 degrees, holding for 7 minutes. So here I enter 7 minutes. Okay. Then we're ramping up at 15 degrees per minute to a final temperature of 240. And then I'm going to hold it there. This wasn't in the method, but I'm going to hold it there, say, for 5 minutes. Okay. So basically, a run is going to be about 26 minutes. So what you have here typically is this is the analytical portion of the method. And then what you need to do, much like HPLC or GC, it's different, is we need to make sure everything is off before the start of the next injection. If everything is not off the column, it will come out in subsequent runs and we'll get ghost peaks, and that's going to cause a lot of confusion and problems. So you want to make sure you have everything off the column. That's why I extended this runtime here a little bit. I could have taken it higher too than necessary. So you want to make sure everything's out off of your column before you make your next injection. Sometimes it's a good idea to run through this program once with no injections, or just shooting a solvent injection to see what it looks like, to make sure that everything's off the column. Okay, so we have this done. Now we come over here to our FID. The FID temperature here was set to 280. Okay, and then you have the stop time here. Now, what I usually do here is the stop time is the same as the run time. So I'm going to set to 25 minutes, not the full 25 point. Because if I go back to the column here, you can see the run time's 25.6 minutes. So we're going to acquire data for 25 minutes. Even if everything is off your column and all your peaks of interest are out, it's still a good idea to continue to acquire the data. By doing so, we can make sure that if there's a problem arising or we see something coming out, we'll know that when we look at the data. The delay time here should be set to 0. Again, there's no need for that. We're not subtracting a detector. Now down here you have your makeup gas flow here, which is 24 mils a minute. Again, that's to keep the peaks sharp. You don't have this makeup gas or these features here due to the fact that your instrument's an older instrument, and but you do have valves on the back of the GC where we can set these things. So then you have your hydrogen flow and your air flow, which are needed for the flame. Okay, so we have that. Then over here in the general here, we're just going to leave these here. We're not going to worry about anything in here. We're going to come up here and say File, Save Method File As. We're going to give it a name here. I kind of skipped this step here, but I'm going to go back and correct myself for it in a minute. And I'm just going to call this one December 5. Save. Actually, what I'm going to do now is I'm going to actually go back a step here, say File here, select Project Folder. Under Project 1, we're going to make a new folder, and I'm going to call that USF, and then December 5. Okay, close, And then I'm going to say File, Save Method File As, and we want to go into that folder. We want to be using that folder that I can't find. Oh, in customer data. I'm using a virtual machine, so things are set up a little differently. But the bottom line is you want to save it to a project folder here. Keep yourself organized. Otherwise, bad things will come down the road. So after you have your method set up here, or B is if you have a method already set up, then you can do File, Open Method File, and then you can just open the method file and run from there. So I'm going to go from here. I'm going to save the method file here as test1, and it's not going to there. You pause this for a moment. Okay, what I did is I reorganized my files. So now when I say File here, Open Method File, there it is. My directories were all mixed up. Say Open. Then usually what I do, the next step here is under Acquisition, say Download Instrument Parameters. So that will download the parameters of the instrument. Now something else to be aware of is on the front panel of the instrument here, of the instrument itself, you have to start the system there. Or make sure you hit this button here, which is turns the GC system on. And that will activate all the heating zones, and you'll hear a difference. So you can either do it on the front of the instrument by hitting the PF1 button after system, or you can turn it on here. That is very critical. If not, your heating zones won't heat up. So at this point, typically what I would do is maybe do a single injection, null injection per se, perhaps. I go start single run. Gonna come down here and I just say solvent. Yeah, I can't spell. SVT, solvent. Whatever, sample name and sample ID can be anything you want them to be. Okay, the method file there is what we have there. This is where it's going to be saved to. Make sure you stay organized, and that's why I went through and reorganized that. This is what the data file name is going to be here. So maybe that's injection one. Then I would say okay. And once everything is ready, you can make an injection and press start here, or you can press start on the GC. And then we'll be acquiring the very first data set. So that's how we get our first data file. And again, the first time through, I would typically run a solvent, or not inject anything. Let's just see what the column looks like, make sure it's baked out, and that there's nothing coming off the column. Okay, so that's how we set up the instrument portion of the run. We're going to talk a little bit more after this. We're going to find some acquired data, and from there, we're going to continue to build onto this method.